All right, so in this video, I want to go over a method that we'll be using in lab that kind of takes some of the ideas that we've seen previously about like mixtures of gases and basically just applies them to a more like experimental and practical approach. So what I have pictured here is what's called a pneumatic trough. Now we've actually used this before in one of our previous labs where we were mixing together bleach and hydrogen peroxide, and from that experiment, what we were trying to do was basically collect some amount of gas, in that case oxygen, so that we could maybe measure things like how much of the reaction actually occurred, right? And kind of using that as basically like our theoretical yield. Now, for that to work, right, what we need is basically a way to capture a gas, which is usually kind of all over the place. And kind of how that's done in this pneumatic trough setup is you have like a container for the gas that is sealed off with water down below it. So in this case, right, we kind of see this like jug that's sitting inside of a big tub, and that jug was actually initially completely filled with water. And as gas is being produced from whatever reaction, bubbles kind of come up into the jug and displace some of that water, kind of shifting it down below. And so, right, when we keep all of the gas kind of in just one place, we're able to then maybe measure the volume of that gas, basically just by using, whatever volume of space is empty in that once filled container. Now, in terms of like really going beyond what we had seen previously and actually applying maybe some of the other properties of gases that we've learned about throughout this chapter, right, we can kind of imagine here how we could use a pneumatic trough like this one to figure out things like, say, the pressure of the gas or other properties of the gas as well. So one of the kind of key assumptions or things that we need to ensure when using these pneumatic troughs is ensuring that the pressure that's inside of our little jug here or in our little collection area, that is equivalent to atmospheric pressure. Now, the way that this is done is kind of by adjusting the height of the inner chamber versus the outer tub, basically making the water line that's like inside the gas container equal to the water line that is outside of that container. And so when we do that, right, we then kind of ensure that like atmospheric pressure is sort of matching in pressure to whatever the gas inside that container has. Um, Now, while the atmospheric pressure does in fact match the pressure inside that container, right, that's not technically speaking just whatever gas was produced from our reaction that is inside that chamber. So, right, the problem here is that like where we maybe produce a bunch of bubbles from our reaction, we also kind of give space for water to also evaporate off and go into the gas phase as well. So although most of the water that's used in this pneumatic trough is kept in the liquid phase, on the surface of that liquid, teeny tiny little water molecules can kind of jump off, go into the gas phase, and now they're part of that mixture up above where the water ends and in that kind of empty space of the pneumatic trough. And so because you then have like a mixture of two gases, right, each is going to exert its own partial pressure, and the total pressure matches that atmospheric pressure, but right, that total pressure includes both whatever gas we produce from this reaction along with the pressure from the water itself. Now, this pressure for the water is referred to as the vapor pressure. This is, for more technical terms, the pressure of a gas up above its liquid phase. So if you have any liquid and there's some empty space up above it, some teeny tiny amount of the liquid will evaporate, go into the gas phase, and being a gas, it's going to exert then some amount of pressure to go with it. All right, so with all of that in mind, right, what I want us to do is kind of consider an experiment where we're using a pneumatic trough like this one. Again, you'll be using this in lab as we've already done in lab, but here we're going to see again like how we can maybe tie all of these different pieces together of the different properties of gases, right, using an experiment like this one. So imagine here, right, I have, say, some reaction as pictured, and basically what we're doing is we're collecting oxygen gas over water using the pneumatic trough. What we find through our experiment is that the atmospheric pressure in the lab room is 728 torr, and the temperature in the container is 22 degrees Celsius. We also find that from this reaction, the volume of gas that's collected is 155 milliliters, and the vapor pressure of water at this temperature is going to be 19.8 torr. So with all of this information, right, I want us to first answer here just how many moles of oxygen gas were produced from this reaction. So, right, taking into account all of these different things, such as the total pressure or the atmospheric pressure, the temperature, the volume, and how much pressure maybe is being accounted for from the water, right? Determine how many moles of O2 are produced from this reaction. All right, so for this example, right, the answer that I got was choice B, 0.00596 moles. So let's kind of walk through exactly how we can get this answer, right, just in case we're missing any pieces of this. So I took away the picture, that way we can have a little bit more space to kind of work through all of this. But right, what we're trying to find is the number of moles, or in our ideal gas law, N. So isolating N from the ideal gas law, we know that that's equal to pressure times volume divided by R, the ideal gas constant, and temperature. So really what we need to do here is find the pressure of the gas, the volume of the gas, the temperature of the gas, and we can then plug all of that into our ideal gas law to solve for N. So starting first with, I guess, finding the pressure of the gas, right? As we have alluded to before, right, the pressure of the oxygen specifically is just part of our total pressure. And so where our total pressure is the same as the atmospheric pressure, right, we need to subtract out from that whatever the partial pressure is of water. So right, really the partial pressure of the oxygen gas is going to be 728 torr minus 19.8 torr, leaving us with just 708.2 torr. Now keeping track of sig figs here, right, when I subtracted, I'm going to maintain significant figures just to the ones place. So rounding that to 708 torr, but because I'm going to use this calculation later, we'll kind of save our extra digit just to avoid any rounding errors. Of course, torr is not like a good unit to use in our PV equals nRT equation, so I do need to convert that into atmospheres instead. So the pressure of the oxygen gas, if I try to convert that into atmospheres, I'll need the following conversion factor with 1 atmosphere over 760 torr. And so that equates to then 0.93184 atmospheres. Again, technically 3 sig figs there, but right, having that as the atmospheres for this reaction instead. But so then, right, we now have the pressure to place into our PV equals nRT rearranged equation. We're also going to need the volume, which we're told is 155 milliliters. Of course, converting that into liters instead would just be 0.155 liters. And then the temperature that we need is going to be in Kelvin. So rather than 22 degrees Celsius, right, we would use the temperature as 295 Kelvin. So I kind of set up here then how I would plug all of these numbers into my ideal gas law equation. And again, the R constant here is going to be provided on your formula sheet, 0.0820576 liter atmosphere per mole Kelvin. But so using that R constant, using my pressure, volume, and temperature all in the correct units, I find then that N is equal to this many moles, right, 0.00596 moles. And so, right, you're going to be using something kind of similar to this in the Sweets lab, right? A similar reaction scheme, basically collecting the gas produced from a reaction in a pneumatic trough. The main difference with the Sweets lab is that we're actually going to be finding out the R constant for ourselves. So rather than using R like we see right here in the equation, what we're instead going to find is pressure, volume, temperature, and moles for a single gas sample, and then use all of those things together to solve for R. So it's a really interesting lab. I think it's a lot of fun, especially to see how we can experimentally reproduce some of these constants that we use in class. But please let me know if you have any questions, and I'm always happy to help. Bye.